Hi, I'm Jennifer from Hyzol. Every successful product starts with a design, and every design starts with a drawing. We know how important it is for our customers to get this right prior to production. Today, I'm pleased to be joined by Keithan, a mechanical engineer at East Metal Dynamics. Welcome, Keithan.
Thank you for having me, Jennifer.
So you are a sheet metal part manufacturer. Could you tell us a bit more about that?
For sure. I'm a mechanical engineer at EM Dynamics in Scarborough, Ontario, in Canada. And it's my duty as an engineer to help bring our customers' part come to real life. So I take that as a task and I input my understandings of sheet metal engineering into these parts and help our customer get what they want on time.
Okay, that sounds great. So taking sheet metal, could you talk a little bit about what the process would be if I was an engineer or a designer who had a product that wanted to get to market and I prepared my drawing, I submit it to you, and what would be the next steps?
For sure. So when our customer submits a file, I'd expect to see both a model and a technical drawing. So within this model, it's either a single part or a multi-part assembly. So when I first get everything, I look into the technical drawing to see what kind of part it is, the overall sizes, dimensions, tolerances, what kind of hardware they're using, any outsourced processes that may be needed. Once I look at that, once I see everything is good there, I compare the technical drawing to the model itself to see if there's full correlation or if there's any mistakes or any inconsistencies that I see. Once everything is good, once I'm happy, I flatten that piece of sheet metal using our company's bend radiuses, bend deductions, and K factors. And once that part is flat, it gets saved as a DXF file. And this DXF gets imported to Radan, which is a software that we use for our laser cutter or our laser punch combo. The thing with Radan is it's a great program when you want to optimize the sheet you're using so that our customer won't have to waste extra money on extra material we might be using. So the customer is getting the cheapest cost for laser cutting. Once that program is created, I also create a work order, and this work order is a technical document that I use to communicate to the shop floor. And here is where I list all the processes, both in-house and outsourced, that this part is going to need for completion. So once I create that work order and send it downstairs, the shop floor workers know exactly what to do with that part and how to bring it from a flat piece of metal to packaged good for the customer.
Excellent. And is there a specific program that you use to do this? What program would you recommend for an engineer or a designer who wants to create their product, especially in 3D? What program could they use to do that?
For sure. So for all of our technical drawings and models, we use SolidWorks.
Okay, could you tell me a little bit about SolidWorks? How does it work? How is that advantageous for somebody to use who wants to create a drawing?
So SolidWorks, the main one that I use is sheet metal, and sheet metal is what we use with our customers' parts to help flatten it. We also create custom designs, and when we create those custom designs using SolidWorks basic features, we convert them to sheet metal so that they could be manufactured. Another feature of SolidWorks that I'm currently using and working on is computational fluid dynamics, CFD. So it's a feature in SolidWorks called flow simulation, and what this does is it helps an engineer see how their part acts temperature-wise or pressure-wise or within a velocity field. So for instance, if I'm creating a heat sink, the engineer can see how hot that heat sink will be and what type of improvements need to be conducted so that the temperature drops faster or drops better. Another key feature of SolidWorks that I really like is the use of equations. I think this is very beneficial for someone who's making designs that are constantly changing. Similar to the previous example, if a person's making a heat sink, equations allow it so that the person could adjust the entire design with the change of one letter or one number. Whereas a person who doesn't use equations would have to go back to that sketch, change the dimension, wait for it to load, hope nothing breaks. So equations really help an engineer time-wise, and which translates to money-wise.
Definitely, most definitely. I think the time factor is very beneficial for somebody who wants to create their product and be efficient. How important is it to have a fully dimensional technical drawing to go alongside that? And how important is it that that's well designed?
For sure. Technical drawings are very important, and in my opinion, it should be always included because the technical drawing is the form of communication between the customer and the manufacturer. So whatever notes, whatever comments that the customer's engineering side wants to make, that's what's provided to the manufacturer. So if there's no technical drawing, the manufacturer's basically lost as to what's gonna happen to his part or how this part's gonna be made. Technical drawings, they convey a lot of important information, such as tolerances, surface finishes, any procedures that have to be made for assembly. Like, these features are not available with just a CAD model. They have to be written in text, which is why the technical document is always important. This is a 3D CAD model that I think every engineer should know because it helps build an innovative engineer as to, like, using SolidWorks, an engineer's possibilities are endless. Anything that the engineer could think of can be put on this CAD program, and they could do any type of analysis they want. They could put it into an assembly if they want. Like, possibilities are endless. And the good thing with SolidWorks is that it has a great user-friendly system, and it's very easy for a person who has no experience to learn. There's a lot of videos that SolidWorks has, both online and within the software itself. Also, in terms of engineering, it helps the engineers see if their part is good tolerance-wise. There's features for simulations. There's features for seeing the cost and seeing if it's reasonable or if it can be improved. So it's a great program for any engineer, in my opinion.
It sounds it, and I do think that being user-friendly, having a nice interface, and having lots of accessible videos where you can go and actually learn how to use this software is really important. So that's really nice. What would you say are the key capabilities of SolidWorks? How do you use it? What does it do?
SolidWorks is just like an open book. There are so many capabilities that it could provide the engineer.
Sounds great. And when producing their drawings or designs, our customers often have a lot of questions on how to get their design manufacturable ready. So in this sense, what should they look out for? How should they check the drawing, whether it's 2D or 3D, in terms of its manufacturability? So is there some kind of checklist that they can use to say, yes, I'm on the right track, yes, I've checked this, it's ready to be sent to the manufacturer? What points could you give us to check for and to look out for prior to sending the design off to be made?
Sure. I can think of 5 to 6 points that an engineer should always look out for. The first one coming to mind would be hardware tolerances. And so when the customer creates a drawing, they create holes for the hardware, and sometimes customers, they go towards the lower end of the tolerance, some go toward the higher end of the tolerance, some are not even within the tolerance. So when you're speccing hardware, always go to the manufacturer, see what hardware the manufacturer recommends, and always go in between that tolerance. It's always important to do so, because if the hole size is too small, the hardware is not going to fit. If it's too big, it's not going to fit. If it's too small, it has to be drilled out. But if it's too big, there's nothing you could do. The manufacturer is always going to check, but if it's 3-4 holes, it's okay. But if it's 300-400 different holes, then it's going to take time on the manufacturer to check all these holes, which also translates to money. Another important factor that the engineer should look out for is to see if there's any features that are near the bend line for sheet metal parts. When you're bending sheet metal, you always want your features within or more than 2 times the thickness. It depends on the thickness and the model. The thickness and the material of the model, but you always want it away from the bend line so that these features don't stretch and go out of tolerance. When a manufacturer looks at this, they'd have to go back to the customer to make sure these changes can be changed, which takes time through emails, which also delays the parts. Another important thing a customer should look out for is to see if the hardware they spec is readily available in the manufacturer's area or even worldwide. Some hardware takes 1 to 2 months just to be made because they're special hardware or they're low quantity. So if a customer needs their part within 3 weeks, it's not going to happen. So here the engineer would see that, and they would opt in for a different hardware that could be available in 1 to 2 weeks or within days. Another factor that should be looked out for is to see if the sheet metal can be unfolded without any interference. Sometimes there's parts where they're unfolded and 2 flanges meet because of the tolerances that's left by the engineer. So always double check once you flatten your part to see if it can be manufactured. Another factor is if you're working on multi-part assemblies, always look out for assembly tolerances, because in CAD, you don't have to leave tolerances because it's a perfect situation, but in real life, you always have machine tolerances. So you always want to leave about 2 thou, 5 thou, depending on your material, so that the manufacturer could lock these into position easily. And the final factor to look out for is to always check your drawing. The manufacturer is going to do so, but if there's a mistake, then the manufacturer is going to have to contact you again just to see, is this right or is this right, which can be saved if the engineer was to just double check their drawing as well as compare it to the model to see if there's any inconsistencies.
Very, very useful practical tips that we can undertake when we have completed our drawing to check its manufacturability. So I just want to summarize those points for our viewers. The first one to look out for is the hardware tolerance. Check the hardware holes and check if they are within the tolerance specified by the manufacturer. 2, check to see if there are any features that are close to a bend, especially for sheet metal parts. 3, check to see if the hardware that you require is readily available, especially if it's possible to be ready within your lead time. 4, make sure the flat of the sheet metal can be unfolded without any interference. 5, for assemblies, make sure that there is this assembly tolerance within the part, so a gap, so that the parts can fit together. And lastly, double check the drawing. This means if there are any problems, and you can catch them before you send it to the designer to be produced, and you can fix that in the early stages. So that was very informative. Thank you very much, Keithan, for joining us, and we hope that you join us again in the near future.
For having me, Jennifer.